Good morning. Good morning, mathematicians. I was surprised at work because for a second, uh, well, it seemed like things weren't working. Um, Upcoming. Is it that delayed? I'm too quick on it. Oh, yeah. What are we gonna talk about today? That's always the question. And I never properly prepare to yap. But there's tons of crazy stuff in my head. We'll think of something. Start off with checking the math news, Reddit. How important are proofs of big theorems? Say I want to improve my proofreading skills. Let's just go to the post. How bad of an idea is it to jump straight to the exercises? Terrible idea. Don't do it. And start proving things after only reading theorem statements. Actually, no, sorry, never mind. That's not true. Definitely, especially when it comes to proofs of big theorems. If it's a little lemma, and if you just, without looking too closely at the lemma, you see that the proof is very short, try it. It might take you a while to come up with the idea. Just because it's short doesn't mean it's not, an interesting, tricky idea. But, yeah, you're gonna need to. It's the theorem statement. It's the proofs of the theorems that allow you to pick up the techniques and the ways of thinking in that field. So, yeah, is there anything to be gained from reading proofs of big theorems? Yeah, it's also, it sort of depends too, right? Like, so with one of the students I'm mentoring right now, we're talking about algebraic topology, and I think our plan, we're going to meet today, I think our plan is to prove the lifting property for homotopies and covers. And the actual proof, I don't know if it's so important. I guess we'll find out. But, I think it's maybe good to really exercise a lot of point set topology muscles. But then, I don't know, is the proof really so enlightening? Like, if you're interested in homotopy theory, is that really building tools you're going to use in the future? Maybe not. But it's always hard to tell, because a proof of a big theorem may contain important ideas that will get reused a lot. It's hard to know ahead of time. Derivation of Gauss. Nice. This is what we need. This is very much in the spirit of my roasting proofs video. This is what we need. We need people just ripping on things. Do we even have anyone in chat yet? Is chat dead? Trying to just justify the steps to derive Gauss' law, including the point form for the divergence of the electric field from Coulomb's law using vector calculus and real analysis, is a complete mess. Is there some framework like distributions that makes this formally coherent? Ooh, major burn. Yeah. Just dunking on our friends over at Our Physics. What a brilliant post. Okay, and then we go into some technical details. Maybe not so interesting to read technical details online, but yeah. Great response. Yeah, love to see it. Love to see it. Great stuff. Great stuff. No, probably not. Especially if we're not talking about Galois. Especially if we're not. I mean, I don't even know. I mean, probably if we told him the setup in terms of groups, then yeah, probably. Nowadays, Galois theory is taught using fully formal language based on field theory. Yeah, and I mean, never mind the Grothendieck's theory of like Galois categories. I mean, would he be able to grasp this modern approach with these? I mean, probably. Probably not understand it better than most professionals in the field. I don't think there's any. No. Because I mean, understanding also comes from, it's not just some immediate, intuitive thing. Like there is various modes of understanding. There's being able to like compute and grasp quickly, and then there's like a deep knowledge and a sense and a general sense of what ought to be true based on your fundamental understanding of the field. Okay, maybe we should go over and talk about some actual math. How do I hide this bar again? Maybe I just don't. Wow, chat really is dead. I'm all alone this morning. This hasn't happened. This is what I thought it would be like my first time streaming, but there was, like immediately 5 people showed up. Okay. Well, since I'm just yapping to myself anyways, why don't I keep yapping about representations of p-adic groups? That's a thing I know about, sort of. So, where were we last time? Oh, yeah. So last time I mentioned we have a combinatorial classification for representations of p-adic groups. We had these things called segments, and truly we need more generality, but essentially everything we could possibly want to know we can really just reduce to the case of half integers, where of course this means an ordered list of numbers increasing by 1. And we articulated a process by which one could attach. So if the length of this segment, the number of things in it, was n, then we could produce a representation, q delta, an irreducible representation of gln qp. And if we could produce that, then we then took a second step and we said, well, now suppose we have R segments. So what we call a multi-segment, because we allow ourselves to have multiple copies of the same segment. Then we would attach an irreducible representation to that. By first, we would consider this. So these are all representations of GLNs, and we just consider a bunch of those GLNs sitting diagonally. maybe there should be a dot 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 there. So this would be GLN1, GLN2, dot 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 up to GLNR. So this is all we view as sitting in GLN equal to n plus all of these things. So we plop each of those representations down the diagonal, and then we would induce that up to the whole group. And my claim was that this had a unique irreducible quotient, and that was the thing that we called, well, I think I called it pi A last time, but I might call it QA for quotient of A. Yeah. One moment. I am going to check to see, I'm going to check if like live stream's working correctly, because it says I'm recording, it says I'm live. I see myself live on my channel. Oh, 8 watching. Okay, so maybe there's someone here. Say hi if you're here, if you can. It's good to know if people are in chat. The usual crew is not here, I suppose, because they do be yapping. Okay. So here we are. We've got these representations. So what does this actually look like? Well, let me tell you one other little theorem that that is going to help us determine. Ooh, yeah, and this is a great example because it actually relates to the perverse sheaves thing I did previously. So we're going to look at these numbers. And we're going to look at the collection of all multi-segments that can be made of these numbers. We're also, so what we're going to do is we're going to start off with, so normally a segment is 2 numbers, but you could imagine, of course, it's just 1 number. Like, to be precise, in the notation above, I should maybe write it as something like 0, 0. But, you know, I'll use a shorthand with just the single brackets to encode this as a single segment. So we're going to perform operations on multi-segments, and the point is that this should correspond to some relationship between the corresponding representations. So what we're going to do, maybe I should explain it more... before I do these computations, I'll do a more illustrative example, shall we say, over on the side here. Pun intended, because there will be a picture. No, I'll do it right below. So the idea is this. So 2 multi-segments, so we'll say delta 1 and delta 2 are linked if their union is a multi-segment. So it needs to be an unordered increasing string of integers going up one by one. So if we had, say, delta 1 was equal to 0, 2, and delta 2 was equal to 1, 5, right? As a picture, we've got like 0 to 2, 1 to 5. So we'd say that these two are linked, right? Because if you took their union, so not their like multi-union, but if you just took their literal union as sets, then it would be 0 up to 5, right? So those would be linked. They would also be linked if they're, we can write it as 0 to 2 and say 3 to 5. So they don't actually have to intersect in this case. And so if they don't intersect, we would say that they're juxtaposed. And then finally, just to give you a non-example, of course, something like 0, 2 and delta 2, 4, 5, right? There would be too big, there's too much of a gap. If we took the union, 3 would be missing, we wouldn't have a segment. And so what we're going to do is a multi-segment we can now perform operations on it. And that operation is you find any two segments that are linked, so say these two, and we create a new segment, B, where we take one of them and replace it by the union, and we take the other and replace it by the intersection. And don't worry, examples are right around the corner. And the point of this operation is the following thing. So if we go back up to this representation here, so this is not the irreducible one, but it is an example. We call it a standard representation. And this has a much more general definition that applies to like other p-adic groups, and there's sort of a larger, more thematic, deeper reasons why we are interested in such things. But for now, we just know that there are things that if we want to go searching for all of our irreducible representations, we need not look further than these induced ones. So take that as motivation if you like. We know that QA shows up exactly once, and in particular as a quotient, but we might be curious about the other composition factors of this representation. So I'm going to call this standard rep. I'm going to call it SA, or sometimes I might even write SQA for the standard representation. And so here's a theorem of Bernstein-Zelevinsky, or it might just be in the sequel paper, which is only authored by Zelevinsky. So theorem, QB appears in SQA if and only if B is less than A. And when I say B is less than A, I mean B is obtained by one or possibly several applications of this simple operation on multi-segments. So last time we actually looked at an example. And you're going to see I'm going to order my segments in a very particular way because, well, we'll get to those theorems. But I ordered my segments in a very particular way. But we looked at last time the segment minus 1/2. We looked at this segment. So in particular, we saw that so I talked about this norm character, nu. I think this is the right way to write it. And it had, I should have given myself more room. But it had a short exact sequence where it had a copy of the trivial representation in here, and the Steinberg as and some infinite dimensional representation we called the Steinberg as its quotient. So this would be Q of just the singleton segment that just contains delta, right? This would be SQ, and I'm going to be lazy and I'm going to drop the set symbols. So this would be the standard representation of delta. And now we talked about how last time, well, we didn't really have a multi-segment description for this thing, right? But there should be some clue here as to, oh, you know what? I've made a silly mistake. I've made a super silly mistake. That's not what I wanted to do at all. Now, in this late hour, I realize the error of my ways. So here's the way it's supposed to go. Sorry. I lied a little bit. Rather, it is this. It is end. Sorry, yeah, there should be 1/2. There should be -1/2. Sorry. This should be the trivial representation. This should be the standard. The representation, the induced representation I explained last time is actually the one that has a copy of the trivial representation as a sub for reasons I explained. But notice I've switched the order of these characters. I've switched the order of these characters, yeah. So, now we can see rather that this is actually SQ of the multi-segment, which has just the segment that is just from 1/2 to 1/2, and the segment from -1/2 to 1/2. And this is Q of that exact same segment. So I would write this as maybe Q 1/2 -1/2. Again, I'll probably drop these set symbols. So if you believe, and you shouldn't really have much of a reason to believe, my multi-segment, my claim about multi-segments and when things show up inside the irreducible representation, then the multi-segment for this had better be the simple operations that we better be the application of a simple operation to this. Well, can we even perform a simple operation on this? We do have two segments, and they are linked, right? If we took the union of these two segments, it would be the segment from -1/2 to 1/2. Those differ by 1. So we take their... so therefore, if this is the segment A, then the simple operation, the segment obtained from it by a simple operation, would be the segment B, which, so the multi-segment, we take the union, and we take the intersection. But since the intersection is the empty set, we toss it out. That was one other little thing I forgot. We don't treat the empty set as a segment. So if it ever appears, you throw it out of your multi-set. So this means that whatever this representation is over here, our combinatorial name for this representation is Q of this segment. That's got to be it, because there's only one other representation in here. But we might ask about the standard representation, SQ -1/2 1/2 of this thing. Well, combinatorially, we can conclude that actually this must also, this representation must be its own standard. Why is that? Well, if we look at this multi-segment, there's no simple operations we can perform, right? And we said that the standard attached to that multi-segment, so this is SQB, right? The only things that can live in there are things of the form QC, where C is obtained by some sequence of operations on B. But but this is impossible. So, okay, if we believe these combinatorial statements, then we know that this is irreducible. We can also see that from the definition of how I said you build Q, right? So remember I said, well, it's going to be, you take all of the segments in here, well, we only have one, and from that segment, you get this representation of of something of length 2, so, or sorry, of GL in the length of that segment. So it'll be this induced representation. And then you take the, so notice already, we're already at GL2, right? So I said you take that, that has a unique irreducible quotient. You take that representation and you break up your group, you put a whole bunch of smaller GLs. Well, but it isn't a smaller GL because this is already a representation of GL2, so we have to put it here. But strictly speaking, we then, perform induction, except in this case, the induction is trivial. We're just going from G to G. So that is just delta Q. Yeah. And that's it. So, it's so weird. There must be something wrong. It's so weird that no one's in chat today. It really is strange. It really is strange. Apparently 11 watching. So, weird. I think I'm gonna leave it there because it's just so much more boring without people in chat. But let me say, yeah. So we have these multi-segments. These are combinatorial gadgets. And we can at least, whatever these standard representations are, if you're willing to believe that they're somehow important to us, we do have this result that at least tells us where, at least tells us how a representation, it tells us, so these things are induced representations. Generally, as we just saw, they can be irreducible, but in general, they will not be. And we would like to know when other irreducible representations show up in there. Well, we do have a condition that says it shows up at least once. We know now, we know for sure now that it will show, like when it will show up at least once. But this doesn't actually tell us exactly how many times it shows up. And so that is the question, is that can we determine, so given any two multi-segments, and let's say B less than A, because that's what we need for this, we know that'll be 0 otherwise, can we determine the multiplicity of the irreducible representation attached to B in the standard representation attached to A? And maybe I'll just leave you with one. I'll leave you with that example that I said actually has to do with a perverse sheaf computation that I did on stream the other day. If we consider the multi-segment, so we start with the multi-segment. We always start with a multi-segment that's all singleton. So it'll be 1, 0, 0, minus 1. And so what are the operations we could perform? Well, 1 and 0 are linked; they're unions of multi-segment. They're juxtaposed, though, right? So the intersection will be the empty set. So we can go 0, 1, and then we'll still have 0 and -1 here. We could do the same. 0 and -1 are linked, so we could perform a simple operation there. It's so funny how I always say I'm about to leave and sign off, and then I don't. We could perform a simple operation there. There's nothing else to do, right, up top, because 1 and -1 are not linked. There's no other combinations that we can make. So now, what can we do with these? Well, 0 is there's a very important condition that I messed up above. Very important condition. We do not say they're linked if one is contained in the other. We want their union to be a segment. Of course, this will be true if one is a subset of the other, but we don't want to consider that linked. Yeah, basically nothing would happen if we did that. I mean, it doesn't really matter, I guess, but the thing is, basically nothing would happen if we took that multi-segment operation between these two segments. Well, the union would just give us back delta 2, and the intersection would just give us back delta 1. So we haven't gone anywhere. So, I mean, technically speaking, nothing's false, but it's just, it's a condition that we ignore because nothing happens. So we don't need to consider these two. We could consider, is there 2 ways to go from here? Hang on a second. Yeah, so we could consider, I'm going to draw it in a certain way, and you'll see why in a second. So we could combine 0 and -1, these juxtaposed. Now notice we could also combine -1 and this other one here. But bear with me for just a moment. So this will be 0, 1. This will be -1, 0. And notice that over here, we can also combine these two. We can combine 1 and 0. And again, we could also combine 1 over here, but wait just one moment. So we get these. This multi-segment happens to be, we can obtain it from both of those multi-segments above. And now finally, I can, if I perform the multi-segment here, because now these are they are linked, right? Their union would be the segment from -1 to 1, and neither is a subset of the other, so we would get -1 to 1 if we took the union, and then the intersection of these two would just be 0, a single 0 by itself, right? And now, notice that this is exactly what we would have gotten if we had done this step. So if we had combined -1 and 0, 1, and then same over here, we would have combined these two. But maybe to keep the diagram less cluttered, because we know it's sort of linearly ordered anyways, like we know the fact that it follows from this one, it'll be less than these two. Finally, if we look at this, 0 is a subset of this thing, so they're linked. There's nothing more we can do. So let me bring to your attention, if you watched my the live stream where I did a very similar perverse sheaf calculation, you should recognize that this is exactly the upside down version, by no mere coincidence, may I add. This is exactly the relation on the closure ordering relation on the orbits of that variety that I wrote down, but simply flipped upside down. And so this is I claim no mere coincidence. Yeah, okay. Here I'm gonna leave it here for now, for real. I guess it turns out I'm not that bored if Chad isn't here, because I love just talking to myself about mathematics. I'm kidding. I miss you, chat. I love you. Come back to me soon. Maybe tomorrow. I don't know where you all went, but hopefully this is the only excuse I'd accept. You're all off proving theorems, and